Very good morning all. I am Dr. Chandra Sadish. I am working as an assistant professor in Department of Chemistry, St. Joseph College of Engineering, Chennai. Today we are going to talk about catalysis. Catalysis is one of the main reactions which are useful to the human history. Many of our pharmaceutical products which are derived through enzyme reactions. In general, a catalysis is a process which alters the chemical reactions rate. So here rate of the chemical reaction is altered through external substance. Okay. Substance. The substance what we have included here is, here the substance is nothing but, here it is termed as catalyst. Okay, catalyst is your substance. Okay, the catalyst, what is the role of the catalyst in chemical reaction? Which alters the rate of the reaction, right? Catalyst can be a gaseous substance, liquid substance, as well as solid substance, right? If the catalyst and substrate both are available in same physical phase, means that is termed as homogeneous. For the homogeneous reaction, homogeneous catalysis, for the homogeneous catalysis, it should be, catalyst should be in liquid form and your substrate also should be in liquid form. Okay, one of the example is H2O2 is getting degraded to H2O. In this reaction, this is the substrate, okay, where we can use dilute H2SO4 as a catalyst. Here the dilute H2SO4 is, is in liquid form, as well as your H2O2 is available in liquid form. So this is your example for your homogeneous catalysis. Both the catalyst as well as substrate both are in same physical phase, right? Okay. Now we are going to see heterogeneous catalysis. Heterogeneous catalyst. Heterogeneous catalyst, here we can have formation of ammonia, which is a Haber process, which is generally called as Haber process. Here the substrates are uh, nitrogen as well as hydrogen. Okay. Here we can have Fe or nickel, we can use that as a catalyst. Here you all people know N2 is in gaseous phase as well as hydrogen also available as gaseous phase, whereas Fe is in solid state. Okay. So catalyst which is available in solid phase, whereas your substrates are available in gaseous phase. So both are different, both are in different phases. So which is heterogeneous in nature. Okay. Homo means same, hetero means different, right? Fine. Next we move on to what are the advantages while going for homogeneous and heterogeneous. What are all the advantages as well as disadvantages we are going to see. Homogeneous, heterogeneous. Homogeneous, the possibility of regeneration of catalyst. Okay, the term is regeneration of catalyst. Okay, the possibility of regeneration of catalyst is low. Okay, because your chemical substances and your substrate as well as your catalyst both are in same phase. After the reaction was over, when we going to remove the product as well as the catalyst, both are in same phase means that too hard to separate. Okay, so regeneration of catalyst is low or least possible. Okay, least possible. Whereas in heterogeneous reaction, the regeneration of catalyst, the possibility is high. Possibility is high because both are in different phases. So after the reaction was over, your ammonia is also a gas, right? In this reaction also, ammonia is a gas and Fe is solid. So we can separate easily, right? So both the physical phases are different, so it can be easily separable, right? So this is the first advantage of heterogeneous catalysis, right? Then the operational temperature, the temperature at which the reaction is undergoing there's a possibility. Okay, at what temperature you can choose a homogeneous one, and what temperature heterogeneous one possibility, right? Here we can go up to room temperature to at least 100 or up to 150 degrees Celsius. Okay. Whereas here in the case of heterogeneous catalysis, we can go up to higher temperatures too. That is almost uh, greater than 500 degrees Celsius also we can go. Okay. There is no no disadvantage while using the solid catalyst over there, right? So the heterogeneous chemical reaction can be used to uh, undergo a reaction up to 500 degrees Celsius, right? Then now we we can move to uh, how the catalysis, how the catalyst are doing its work. Okay. How in general, how the catalysis is doing its work, right? Now first we need to know, this is in terms of energy. Okay. In terms of energy, your always reactant are going to change as a product. You always know, always when the product is lesser in energy, it becomes highly stable. Okay. So if product is lesser in energy, then only the reaction will undergo, right? This is called energy barrier. Okay. This is called energy barrier, right? Then this one is called uncatalyzed reaction, right? Whereas the same case, the barriers will be same. Okay. This is like your reactant, this is like your product, reactant, product. Okay. But the energy required to pass through the barrier will be reduced when we use catalyst. Okay. This is called catalyzed reaction. Okay. For better understanding, I have used this thing. Okay. This is time. Okay. You can incorporate that catalyzed reaction here too. That is same process, but the energy of activation is less and it will reach the same product, right? Right. This is the advantages of using catalyst. Okay. Fine. This is called energy of activation. Okay. Right. Fine. Next. criteria of catalyst. Okay. In general, catalyst which will not initiate reaction. Okay, will not initiate the reaction. Will not initiate the reaction. Catalyst is a supporting material. Okay, which will not enhance. It will not initiate the reaction. That is the first point. Will not initiate the reaction. Okay, and at the end, of the reaction, catalyst should be chemically unchanged. Okay, the color of the catalyst may be changed over the time after the reaction was completed, whereas its chemical nature will not change after the reaction too. Okay, then only you can term it as catalyst. Otherwise, it is used as a substrate. Then only we may that belongs to different kind of reactions. Okay, and in catalysis, it should be chemically unchanged after the reaction was over, right? And in general, catalytic reactions are more specific in nature. Okay, how specific? Specific in nature, which is when we use same substrate but using different catalyst, we can get different products. Okay, so the possibility of using a metal, that is using a same substrate, same substrate. Okay, but same substrate, but we can get different products. Okay, so always your catalysts are more reaction specific. Okay, this is like your product can be one product can be alcohol, another product will be aldehyde, like that. Okay, so both the products will be different when we using different catalysts. So if you are using copper as a catalyst, means it will follow a different pathway, and nickel will follow another pathway, another reaction pathway. Okay, optimal pH is also required. Optimal reaction temperature is also required to undergo a catalytic reaction. Okay. Next, we move on to autocatalysis. Okay. You know what is catalysis, right? The catalyst which are going to alter the rate of the chemical reaction, right? Here, the catalyst is the formed product. Okay. Your catalyst is a same formed product, which is ethyl acetate on hydrolysis is going to form a product which is acetic acid and then ethanol, right? Acetic acid and ethanol. Here your acetic acid, that is CH3 COOH, work as a autocatalyst, work as a autocatalyst. In this condition, this is your reaction coordinate. Okay, this is by time. Here, at the initial phase of the reaction, your product is slowly formed. Okay, after some time, your acetic acid is formed means the rate of the reaction will be more and more and more. At the end of the end phase of the reaction, your rate will be more and more, right? So your plot is like this. This is the end of the reaction. So your rate is end of the reaction, rate is high due to presence of acetic acid. So your acetic acid itself acts as a catalyst over there, right? So at the end of the reaction, or the final phase of the reaction will be more and more and more faster compared to initial phase of the reaction, right? This is termed as autocatalysis. Your decomposition of arsine also belongs to same category, right? Belongs to your autocatalyst category, okay, where arsine, the formed arsine from arsine substrate is we can call it that as a autocatalyst, okay. Okay, catalysis types I have discussed, right? That is homogeneous, heterogeneous. Then another important and the third biologically important, as well as more and more pharmaceutical industry also we are using this type of reaction, which is enzyme catalysis. Okay, enzyme catalysis, right? You know what is catalysis? What is enzyme? Enzyme is type of protein molecule. Okay, this type of protein molecule, which is large molecular weight, which has large molecular weight. Okay, and enzymes are derived from natural organism. Okay, where why we are in the need of enzyme catalysis. Okay, enzymes are more. I have already said that in general catalysis are more specific in nature. Okay, enzyme catalysis is more and more specific in nature. Okay, this is more specific in nature. Okay, uh, in your higher study higher secondaries also, you can see that yeah, your enzyme substrate, then your intermediate will be formed. Okay, uh, through lock and key mechanism, they can interact. What is lock and key mechanism? This is like enzyme which is this is like this is the shape of the enzyme means your substrate will be locking in this part of the enzyme. I have already said that this is like large molecule. Okay, this is your comparatively your substrate is very much smaller in size. So the reaction will be your substrate is here, then this is your X. Okay, so this is how your enzyme catalysis will be more and more substrate specific as well as product specific. Okay, catalysis always found a specific path for reaction to undergo. Okay, right. Next, we move on to um, enzyme catalysis. Enzyme catalysis rate of enzyme catalyzed reaction. Okay, Michaelis-Menten reaction or equation, we can term that as a Michaelis-Menten reaction or equation. Okay, the enzyme catalyzed reaction rate was how we are going to derive the Michaelis-Menten equation. Okay, now let us consider enzyme which is going to react with substrate and form a intermediate complex. Intermediate complex. Here your enzyme is there, substrate is there, and formed a intermediate complex. Okay, the reaction, uh, the reaction the rate we use rate constant K1. Okay, in this reaction we use rate constant K1. Then your your enzyme and the substrate uh, are combined together and formed a intermediate complex, uh, which is not so highly stable. Okay, which will be degraded easily into a product as well as enzyme and substrate too. So for the reverse reaction, that is your X, right? That is the intermediate complex. Then that will again change it back to enzyme as well as substrate. Here the rate constant will be taken as K2, right? Your intermediate complex, what I have mentioned is, can be slowly formed as a product too. This is called disintegration. This is called product formation. Okay, here the rate constant what we are going to take is K3. Okay, this is your product formation. And you know, this is the slowest reaction which is possible in this three reactions. Okay, your product is slowly formed. That is what here we are mentioning. Okay, here where E is enzyme, S is substrate, your X you know, that is intermediate complex. Um, intermediate complex means E as well as S combined, right? That we can call it as X, right? So E S is just interlocked like that. Okay, that is the intermediate complex. Okay, so these are all the terms, that is enzyme, substrate, as well as intermediate complex also there, right? Your rate of formation of intermediate complex can be derived through differentiating your formation of X. The symbol we are going to use is molar concentration of X, okay, with respect to time, right, which is at the rate constant K1 we are having enzyme as well as substrate. Okay, this is the formation of X, right? So we are going to use positive sign. Okay, there is a disintegration or degradation of X, where we use minus symbol, that is K2 X is degrading, right, or disintegrating, as well as K3 of X. So this is formation of X dissolve disintegration of X. Okay, we just rewrite the same here. You are just taking out X, then remaining is K2 plus K3, right. This is the formation of this is the rate of formation of intermediate. Okay, this is the first thing, right. Then another formation also was there. What is that? That is the product, right. Rate of formation of product also there, right. In that direction, your rate can be derived from d of E divided by with respect to time, right. That is your K3 into X. Okay, this is the rate of the formation of product. This we are differentiating with respect to time, right. At the initial phase of the reaction, that is your unreacted enzyme, that is your E naught. Okay, unreacted enzyme why we are using this marks means this is the molar concentrations, right. Molar concentration of unreacted enzyme, which is equal to this is your initial concentration of enzyme. This is your unreacted enzyme concentration, right. Your initial will be accounted through unreacted enzyme concentration plus which is available in intermediate complex, right. This is your concentration of intermediate complex. Okay, enzyme concentration of intermediate complex, right? From that, we are going to find the concentration of E, which is nothing but initial concentration minus X, concentration of uh, enzyme in the intermediate complex, right? We are going to substitute uh, the E value here. Okay, let us take this as your equation number 1, and you can take this as a equation number 2. Okay, so substituting the value in equation 1, that is K1 into E naught minus X, then S also there, right, minus X of K2 plus K3, right. Okay, this is equal to d of x divided by dt, right? D of x divided by dt. Your you know uh, intermediate complex is highly unstable, right? So it will easily uh, disintegrating as a product, or disintegrating into enzyme as well as substrate, right? So we can take dx by dt equal to 0, right? Considering dx by dt equal to 0, um, because of intermediate is unstable. Okay, so that will be too minimal. Okay, so dx by dt equal to 0, so we can substitute here. So this value going to be 0, right? So K1 into E naught, then I'm substituting S2, then minus K1 also coming inside, K1, then X also there, your substrate also there. Okay, K1 into E naught into S, then K1 into X, then S also there, then minus X, then K2 plus K3 also there, right? so which is equal to 0, right? So we are uh, going to separate based on that. Here K1 E naught and S will be in one side. We can take X, right? So upon taking X, we are remainder of K1 K1 S S K2 plus K3 also there, right? K1 into S was there and K2 plus K3 was there. So K1 to E naught in X equal to K1 then S plus K2 plus K3 into X, right? So we are taking X on one side. Here this part is going to denominator, that is K1 E naught then S divided by K1 S plus K2 K3, right? We are having X value by dividing K1 S. Let us take dividing X by using K1S, which resulting your K1 and S will be cut off, that is remaining part is E naught, right? Here also K1 and S will be there, your K1 and S will be cut off, right? Let's write in brief. Okay. K1 E naught into S divided by K1 into S, right? Divided by K1 S divided by K1S plus K2 K3 divided by K1S. Okay, so K1S cancel, K1S and K1S is cancelled. Okay. So this will be useful later. So I kept here, then followed by your E naught will be remaining. So E naught divided by 1, this will be cancelled. So remaining is 1. Then K2 is there, K2 plus K3 is there as a whole, K1 and our concentration of substrate is there, right? What will be equal to is X, right? Now on substituting X in equation 2 is here, that is dP divided by dt equal to K3 and X will be there, right? So X is not more concentration into 1 plus you can write here too, no, not an issue, 1 plus K2 K3 divided by K1 into X, right? I can this bracket 2. Then we are simplifying more. Just a moment. K3 will be there, your E naught will be there, there will be 1 plus these 3 factors. That both the 3 rate constants can be cumulatively called as Michaelis-Menten rate constant. Okay, so here we are taking Km. Okay, Km is nothing but K2 plus K3 divided by K1. Okay, so K M divided by S, right. Then we are substitute, we are going to multiply both numerator and denominator using S. Then it becomes K3 E naught S divided by S plus Km. Multiplying both the numerator and denominator using S, we are having rate of the product equal to K3 into E naught into S divided by S plus Km. S will be cancelled, so we are getting this thing. Okay. This is called as Michaelis-Menten equation. Okay. So what you have seen over here is we are going to finding the sorry we have find the rate of the enzyme catalyzed reaction, uh, where enzyme is termed as E and S termed as substrate, and then the intermediate complex which formed is uh, termed as X, then product was termed as P, right. uh, your final rate of the reaction can be calculated through this equation, which is K3 into E naught into S divided by molar concentration of S, then plus uh, Michaelis-Menten constant Km, right. Right. At these are all the conditions, the possible conditions of substrate concentration. Okay. At lower concentration of substrate. Okay. At lower concentration of substrate, that is S is very much less than Km. Okay. Your S concentration is too much lower when compared to Km value. Okay. So your reaction becomes, sorry, your rate becomes K3 E naught S divided by S becomes almost negligible. Okay, your Km. Okay, so at lower concentration of substrate, it follows the first order kinetics. It follows the first order kinetics, right? It will be following the first order kinetics. Okay, this is your condition 1. The condition 2 is at higher concentration of substrate. Okay. At the higher concentration of substrate, your S value is comparatively very much larger than your Km constant value. Okay. So your equation becomes K3 E naught will be there, substrate will be there, divided by substrate will be there, and Km will be negligible, right? The substrate will be there, Km value is going to be 0, that is negligible. Okay, so S and S. So the concentration of substrate becomes in not valuable. Okay, so which is our rate will be directly falls into 0 order category. Here it will, the reaction with the concentration of higher concentration of substrate will fall into 0 order kinetics. Okay, 0th order kinetics, which is the thing. Okay, why these things are happening? Okay, at lower concentration of substrate, your enzyme has more receptor places. Okay, there is vacant receptor spaces was there in the in lower uh, lower concentration of substrate, because there is a vacancy. When we are adding more and more substrate, it is directly influencing the substrate concentration is influencing the rate of the reaction. So there is a vacancy in the enzyme. All the receptor spots are not already bonded. So when the concentration of substrate is getting increased, the reaction will depend on that. So your rate also depend on the substrate concentration. Okay, whereas in the case of higher concentration of substrate, your enzyme is already fully occupied. The vacant the receptor sites are already occupied. So uh, your rate was not going to be going to increase on further addition of substrate 2. So your substrate concentration won't won't increase the rate of the reaction. Okay, already all the receptor sites of enzymes are fully occupied. So there is no further increase in uh, further increase in rate of the reaction. So it all automatically falls into 0th order kinetics. Okay, so there is no interaction between the substrate concentration as well as the rate. Okay, there is no direct relationship. Okay, it follows the 0th order kinetics. Okay, okay. Uh, uh, for this, up to this, I am discuss about the catalysis, and then autocatalysis, and then what is catalyst, what is homogeneous, what is heterogeneous catalyst, then what is enzyme catalysis, and how the rate of the uh, reaction which is catalyzed by enzyme going to be derived using a Michaelis-Menten equation. This is a Michaelis-Menten equation, and then the conditions are already discussed. First one is lower concentration of substrate is involved, and then second one is higher concentration of substrate was involved. So using this type of Michaelis-Menten equation, we can derive the rate constant of rate of the reactions will be uh, usefully calculated. Thank you for your patience and time. Thank you.